Okay, good morning, everyone. First, I want to make an announcement. Won't have office hours at my usual time today. Usually on Monday, Wednesday, Friday, it's between 1 and 2:30. Today, I have, things going on all the way up to 4 o'clock. So office hours are shifted from 1 to 2:30 to 4 and 5, or between 4 and 5, okay? So I'll be in my office between 4 and 5 p.m. If you have a question you need to get answered before 4 o'clock, you send me an email. I will be monitoring emails and I will be able to reply to those, okay? So in-person office hours will be between 4 and 5 p.m. And then after 6 o'clock, I can meet on Zoom, okay? So that was the only announcement. With regards to this class, today's class, I will cover node voltage analysis. We'll go over the methods and the steps. Then I will go over an example problem in detail. And then homework for node voltage analysis is due on Sunday. It consists of only 3 problems. I will create a short video regarding each one of those homework problems, and I will post it online. And I will also post a slide in the class notebook, so you'll have that. But again, it's 3 problems. It shouldn't take longer than an hour to solve that homework. The reason I'm mentioning this is because we will have quiz on Monday, as usual, and that quiz will be based on the topic of node voltage analysis. Okay, so again, ask as many questions as you can or as you want in today's class. Okay, all right, let's get cracking. Let's see. Node voltage analysis. We introduced the topic last class, and is this section 4? I believe it is. Hold on. Chapter 4, yes. Okay, so let's go here. Now, the goal of circuit analysis is to determine the unknown voltages and currents in a circuit. In this case, we have resistors in a circuit, so we wish to determine the unknown resistor voltages and unknown currents through those resistors when we apply a source. So to perform a mathematical analysis and to solve for these quantities, we need mathematical equations. In this case, it would be a set of linear equations of the form ax plus or minus by plus or minus cz equals d, where a, x, y, and z are your unknown variables. In node voltage analysis, those unknown variables would be your node voltages. Okay. Nodes, electrical node, again, to recap, is any place in a circuit. It's a junction of 2 or more components. Node voltages would be measured with respect to a reference point. So we discussed this in last class where I said we pick a reference node to measure all other node voltages, right? Now let's look at how we will apply that to a network of resistors. So we have 2 examples. An example above, we have a single resistor with a value of R. The nodes are already labeled. The node voltages are also labeled. When we begin analysis, this will not be the case. You will be responsible for labeling the nodes and assigning node voltages. So this example, I can write that I have voltage VR, voltage across the resistor. And in terms of Ohm's law, I can write this is I times R. The current I through the resistor is also given to us. But when you solve for an unknown circuit, this is an assumption that you would have to make. Okay, again, we will explain that when we get to the example problem. So from here, I can write I equals VR over R. And at this point, I will ask you, if the current is going from A to B, which end is positive and which end is negative for the resistor voltage VR? Which end is higher? I heard some murmurings of A. How about some nods or some shakes? Nods, okay. So let's see, plus and minus. That conclusion is because of the current direction. The current direction is something that you will choose. You will assume which direction you want. Okay. In this case, it's given to us, and I can write out the resistor voltage VR in terms of the node voltages. Make sense? So you have resistor voltage. The resistor voltage will be described in terms of the node voltages at either end of those resistors. And the polarity of that voltage will be given or concluded from the current direction that you choose. Make sense? Let's apply it to a larger network of 3 resistors, R1, R2, and R3. Again, in this example, the nodes are labeled A, B, C, D. Node voltages are labeled VA, VB, VC, and VD. And current directions are already given to us. So if I1 is flowing from the left, which node is higher for resistor R1? VA is higher, right? So plus minus. So we got plus minus here. R2 is connected between B and C. Current's going from the top to the bottom. So which end is higher? B and C. So we have B as plus, C as minus. How about R3? Plus, minus. How come we have a minus and a plus at the same node? Exactly. That plus, minus, minus do not belong together. Okay, I'm talking about node B. Node B has a minus and a plus, but they have nothing to do with each other. The plus and minus belong solely to that resistor itself. It does not affect anything else. It's simply an indication that which terminal of that resistor is higher than the other terminal. That's all. So if I was to write a KCL expression at node B, I would obtain I1 entering the junction and I2 and I3 leaving the junction. Online students, if you have a question, please speak up. Do not type in the chat, okay? The speakers in the classroom are on at a loud volume, so I'll be able to hear. Apply Ohm's law, and I can write VR1 divided by R1. Actually, let me note down VR1, VR3, and VR2. This will be VR. Then VR2 divided by R2, and I3 is VR3 divided by R3. I would say do not skip this step. Students tend to skip this step. Even textbooks that you might read, you will not see this step. Okay, they will directly write out the next step. I would strongly recommend students do not skip this step. You take your KCL expression, then you take each individual current, apply Ohm's law to each current, and you write out in terms of the resistor voltage and the resistor. So I1 is VR1 over R1, I2 is VR2 over R2, and I3 is VR3 over R3. This will minimize errors in your solution. Oftentimes, you might feel that you do not have enough time. But again, I would strongly recommend do not skip this step. Okay, so based on my current direction, what is VR1 in terms of node voltages? Current's going from left to right. It's going from A to B. So it's VA minus VB. VR2 is going from B to C. So it is VB minus VC, and VR3 is the current for I3 going from B to D. So it BB minus VD divided by R3. Okay. Now at this point, we will plug in all of the known values that are given to us in the problem statement, meaning the resistor values, the voltage for a source, maybe a current source. You plug in all of those known values in the circuit. You reduce it to a linear equation. Okay. This is the most important part. Circuit analysis goes up to here. After this, it is high school math. Okay, once you plug in all the values, you have a set of linear equations. You simply solve those. And when you solve those, you can use any tool you want. You can solve them manually. You can solve them by plugging it into a programmable calculator. MATLAB on your smartphone or your tablet, plug it into MATLAB. Do not have time to show this week, but I will do that next week. I'll show you how you can program it into MATLAB. Okay, but so far so good. Any questions? Yes. Yes. Mm-hmm. And we will see that in the example next. Yeah. So, oh, summary. I always forget the summary for some reason. First step is identify all the nodes, label all the nodes, and let me write it cleaner. Label all nodes and node voltages. If this is done correctly, if the first step is done correctly, and then of course each subsequent step would just follow correctly, then that's half your solution. Your problem setup is the most important. If your problem setup is not correct, then the rest of it doesn't matter. So again, identify all the nodes, A, B, C, D, E, F, G, label all the node voltages. Doesn't really matter what you label them. You could have nodes 1, 2, 3, 4, 5, 6. Name it after your favorite characters. Doesn't really matter. Okay. Then you assign branch currents to all branches. This is an assumption. You are assuming, again, it's circuit analysis of unknown quantities. You have no idea which direction the current is flowing. You are making certain assumptions, but you stick with your assumptions to the end of your analysis. You do not change your assumptions if your answer turns out to be negative. Okay. And again, the example I've chosen on the next slide specifically addresses all of these points. Okay. So then you choose a reference node after that. Sorry, you choose a reference node before that. That reference node will have a value of 0 volts. Only one student was paying attention last class. Reference node is the baseline. So the reference node doesn't matter what value it has for the purposes of that specific analysis, that reference node will have a value of 0 volts. Okay, doesn't matter what you choose. Then you apply KCL at each node, express each resistor voltage, each current in terms of the resistor voltage, and then finally express each resistor voltage in terms of the node voltage. So let's see how we will apply these steps to this example. The first question I will ask for 5 points is how many nodes do we see in the circuit? It's not a verbal quiz. I was kidding about the points. So feel free to speak up. You're not going to lose anything. If you speak up, you'll learn. Yes. 6, half a dozen. 3, just 3. I count 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Who wants to go for an even dozen? A node is a junction point in a circuit that connects 2 or more components. And you may have heard me say this repeatedly, even in the lab. A wire Can be a dot, can be a short wire, can be a long wire. 100-foot long cable is still the exact same node. If there's nothing connected between 2 points and there's just a wire, it's still the same node. So how many nodes do we see? I see, or well, I hear murmurings of 3, going once, going twice, going, gone. It's 3. You were right on the first answer. 1, 2, and 3. Let's take 10 seconds while you look at it. Again, if you see a dot in a circuit diagram, the dot indicates it's a connection. So yes, it's a node. Then you see another dot in the circuit diagram. Do you see any component between the 2 dots, between the 2 nodes? If there is no component, just a wire that connects both those dots or both those nodes, then the exact same node. That's the conclusion. So if you see multiple dots in here, the reason is because circuit diagrams are created to give a nice, clean, even look. So every component in a circuit diagram would be either vertical or would be horizontal, as you see here. Every component is drawn either vertically or is drawn horizontally. Okay, that's the reason. So identify all the nodes in the circuit. We'll label this A, label this B, and label this C. We will choose a reference node. In this case, I wish to choose C. Ignore this ground. We don't really care about that. We don't. It's absolutely unnecessary. So I will choose C as my reference, and that would mean that VC is 0 volts. How many unknowns in the circuit? A, B, C, 3 nodes. C is 0. How many unknowns? How many equations would I need? That's it. I could apply KCL at any node. I could apply KCL at A, B, or C. Okay, the trick, well, not the trick, but the suggestion is you look at each node. How many connections do you have at that node? Because the number of connections would give you the number of terms in your equation. 2 connections, 2 terms in the equation. 3 connections, 3 terms. 4 connections, 4 terms. So you want to minimize the number of terms, right? A and B both have 3 connections. C has 4. All right, one more thing before I draw this. Can we identify any connections in series or in parallel? Any connection in series? Yes, which one? In series or in parallel? In parallel with R3, but it's not a combination. Okay, so the answer is correct. First part of the answer is correct. Second part, not so much. So if you take a look at I1 and R1, they are connected between A and C. So these two are in parallel. R4 is not connected to A. R4 is connected to B and C, which is also I2. But more importantly, between A and B, we have R2 and we have R3. It doesn't seem quite obvious, but if we look just at the nodes, we can see it is connected between A and B. And so I can state, I'm going to combine those, and I would state resistor R23 is R2 parallel R3. For node voltage analysis, it does not matter as much. Okay. Here, what we're going to do is we'll reduce the number of currents, because if we keep them independent, I would have IR2 and I would have IR3 unnecessarily. I would introduce an extra term, right? So if I combine them, then I have one less current to worry about. I reduced my analysis, one less section. Specifically, if you have something in series, if you have two resistors in series, there is a node in the middle of those two resistors. That is an unknown variable. So if you combine those two resistors together, then you have eliminated one unknown variable. Does that make sense? Right? So we combine those together. I'm going to say this is 2 times 10 divided by 2 plus 10. It's kilo ohms. So it's 1666.667 ohms. Now I'm ready to draw my circuit diagram. So I'm going to make it large. And when students show this to me in the quiz and in the final exam, I want you to draw out large circuit diagrams. Because you have to note all quantities on there. So let's see, one final thing remaining is the current source on the right. Yeah. Okay, I1 is going up, I2 is going down. I1 is a current source. The value is given to us 10 milliamps. I2 is also a current source, value of 50 milliamps. R23 is the parallel combination of R2 and R3. And now this is R1, R2. This is node A. This is node B. I will note this as VA, VB. I would strongly, again, I would strongly recommend you note down the node voltages at each terminal. This will, again, minimize your errors when you're trying to write the expressions. And this is node C at the bottom. This is VC, which is equal to 0 volts. So that's the first step. Identify all nodes in the circuit, label all the nodes, label all the node voltages, and choose a reference node from the previous summary slide. So we have done that. Now, yes. 3 sections, 3 classes, third time. Thank you. Yes. Sure. Yeah. So if we go here to the original circuit, you see R2 is connected to A and B. And between A and B, we also have R3 right there. So if two components are connected to the exact same nodes, they would be in parallel. Again, as I said, it's not, if we don't combine it, it doesn't mean that our solution will be incorrect. It only means we'd have to actually do extra work. I would write out a current here, I would have a current here. So I would have an extra term for every expression. That's all it would do. So combining it just allows us for a more efficient workflow. Okay, where was I here? Oh, so the first step is done. Second step, assign branch currents for every single resistor. Now, at this point, it's not given to us, so we make assumptions. I1 is going up. That's I1. Splits in two. Some of it goes down this pathway, some of it goes down this pathway. That's the assumption I want to make. You can choose the opposite direction. It does not matter what direction you choose. Again, these are assumptions that are based on rules and some logic, but you can go against the rules, you can go against logic and choose the opposite direction. Your answers will not be incorrect. Whatever assumptions you make, you stick with those assumptions to the end of your analysis. That's the most important thing. So I will call this IR1. I will call this current IR23. And just to keep things consistent, I will choose this as IR4 going down. And then, of course, I have I2 going down this way. Okay, IR1, IR23, and IR4. What else is remaining in the setup? What else is remaining? It's not listed here, but I stated that on the previous slide. Voltage polarities for each resistor. If IR1 is going down through R1, which end is plus and which is minus? A or C? A is plus. Current is going down, point of entry is plus. The way to remember this would be to look at the current direction. You would say IR1 is flowing from B to C. So B is plus, C is minus. If IR23 is flowing from A to B, A is plus, B is minus. Make sense? Right? So I noted the polarity and I will note the voltage name as VR1. Here it is plus and minus up top, and I will call that as VR23. For R4, I would have plus up top, minus at the bottom, and I will say VR4. That polarity has to match up with the current direction that you chose. If you choose the opposite direction, then the polarity would be opposite of what I have noted here. It does not matter. But again, you have to be consistent, right? You make one assumption, then the next conclusion arrives from that assumption. This is the problem setup I want to see from students. Okay, this is half the work done. If you have all of this in your circuit diagram, I can immediately look at it and know whether your work is correct or not. Okay, if this is not correct, the rest of the work does not matter. Yes. Oh, we chose VC as a reference. No, that's irrelevant. That's why I crossed it out. So the question being asked is, why is VC 0 volts? The answer is VC is reference, and it has nothing to do with the ground symbol in the circuit. I will explain at the end of the solution what would happen if you chose A as the reference, what would happen if you chose B as the reference. There's a specific reason I chose C as the reference. We will see that when we arrive at the final answers. Okay. All right, so now I'm ready to apply KCL. So as I said, we can apply KCL at A, B, or C. I'm going to choose only A and B because we have two unknown variables. I only need two equations. So I would only apply KCL twice. So let's apply KCL at A. KCL at A gives me one current entering. So I1 enters and IR1 and IR23 are leaving. Okay, IR23 are leaving. Let's see, it's 11:38. I'm going to speed up a little bit. So once I have my KCL expression, I would apply Ohm's law. I1 is a constant, it's a constant current source. I'll leave that alone for now. I apply Ohm's law to the resistor currents. So I obtain VR1 over R1. I obtain VR23 over R23. Now, and again, I strongly recommend that students do not skip over this step. You apply Ohm's law and you write it out. Resistor voltage divided by the resistor, VR1 over R1. Now, the third line should be the node voltages in place of the resistor voltages. And then you also at the same time, you plug in all known values. Okay, so the known values to me is the value of I1. It's 10 milliamps, so 0.01. VR1 is VA minus VC because current for R1 is flowing from A to C divided by 1000 plus VR23 is VA minus VB divided by 1666.667. From this point, it's high school math. I'm going to multiply this entire equation by 1000. That gives me 10 equals VC is my reference. VC has a value of 0 volts. So VA minus VC is simply VA. So it's VA divided by 1000 times 1000 gives me VA. And this would come out to be 0.5999 times VA minus VB. And reduce and rearrange the terms. I would obtain 1.5999 VA minus 0.5999 VB equals 10. I'm going to call this as equation 1. KCL at B is going to give me what does it give me? It gives me IR23 coming in and IR4 leaving plus the current source I2 leaving. Okay. Node B is the junction on the right, far right. Apply Ohm's law and you obtain VR23 divided by R23 equals VR4 over R4 plus I2. Plug in all the known values and the node voltages at this point. I get VA minus VB divided by 1666.667. VR4 is VB minus VC divided by 2000 plus 50 milliamps, 0.05. This time I'm going to multiply it by 2000. And so I would obtain 1.199 VA minus VB equals VB plus 100. Rearrange the terms and I would obtain 1.1999 VA minus 2.1999 VB equals 100. I'm going to call this as equation 2. Solve equation 1 and 2 using any method you choose. I have it solved and my answers our VA is minus 13.569 volts, and VB is minus 52.857. That's the answer. And I will tell you that answer is correct even though it is negative. Wait for a few minutes, a few seconds while everybody writes it down, digest these steps, and let me know if you have any questions. Yes. Yes. So you're talking about this step from here to here, because VC is a reference, VC has a value of 0 volts. And so when we plug in the values, VC 0 gets eliminated. Yeah. Yes. Okay, the question being asked is if the current, since the answers are negative, does it mean the currents are going the opposite way? The answer is yes. But let me draw this out. Yes. Okay. Okay. All right. So let me draw this out. So minus 13.569 minus 52.857. What is my reference point? C. C is at. So what does that mean? If I draw a 2D diagram with the 3 points in the graph and the levels of the points on the y-axis, where are A and B? They're underwater, below sea level. That is C. That's a joke I read from a long time ago. Johnny, how are your grades? Dad, they are below sea level. And this is where A is. 13.569. Because this is a graph, I'm illustrating the minus sign as below. So I don't have to put a sign on that magnitude. Okay, it's below. And then, of course, B is somewhere here. B is actually the value of this arrow is 52.857. So that's more accurate. If the students on the right side of the room chose C as the reference, these are the values they would obtain. VA and VB would be 13.5 volts, 52.8 volts, minus. If the students on the left side, well, from my perspective, on the other side of the classroom, chose A as the reference. So if A was my reference, then VA would be equal to 0 volts. In that case, the answers that you would obtain for C would be 13 point, well, not 52, sorry, 569 volts. The value for VC would not be 0, it would be plus 13.569. So the other side of the classroom would obtain VB as it's not an arrow. B is 39.398. Hopefully, that is the right answer. And so VB would be minus 39.398 volts. The graph The values are different, but when you plot the graph, it will make sense because it just displays you the levels of the three voltages. That would not change. The levels of the three voltages, VA, VB, VC, they are relative to each other. So that does not change. What will change is the values you obtain for that specific node voltage, depending on what your reference point is. And the graph or the chart indicates that. Take 10 seconds, think over that. Yes.
So for your nodes that you selected through the current law, did you use the junctions that were between R23 and R1, and then R4 and R23?
Yes.
Could you have done
So,
that from the
yes. So you're saying, can I apply KCL at this node, right? Yeah, you can do that. The reason I didn't, again, is because there are 4 terms in there. I mean, it's going to be 2 constants. We have 10 milliamps and 50 milliamps. So it would be 50 minus 10. But again, it's 4 connections. So intuitively, when you first start solving it, the point is to be as efficient as possible. So we reduce the unknown variables. We reduce the amount of currents we have. We reduce the amount of node voltages we have in the circuit before we begin writing our equations. And so that's what it is. So again, you have the answers, right? You have the answers, you have the levels. You also know what answer you would have if you choose a different node as reference. So you can choose a different node as reference. You solve it. The equations may or may not change depending on which direction of current you take. Okay. If your reference node is VA, then VA is 0 volts. But if your current directions are still the same as the one in the problem, the equations should still remain the same. And your answers you obtain should match up with these on the left. You could also choose B as your reference. If you choose B as your reference, then VB is 0 volts, and VA and VC would both be positive. But the distance between those points, that would not change. As an example, if you try to find VR4, VR4 is connected between, what is it, VB and VC. And our assumption was VB is at higher level than VC. We still do not change that assumption. VR4, if you wish to calculate, the equation according to our assumption would still be VB minus VC. We do not change that. If you change it at this point, your answer will turn incorrect. You don't want to do that. You still stick with those assumptions. So VR4 is still VB minus VC. That would simply mean it's minus 52.857 volts. And this way you can find any resistor voltage in there. Once you have the resistor voltage, you can find the resistor currents that are flowing through there. IR4 will simply be VR4 divided by R4. Does that make sense to everyone? Okay, so I will post the lecture video shortly after I reach my office at 12 noon. Because after that, I will, I'll just be busy until 4 o'clock. So I'll post the lecture videos, review the solution again. If you get stuck anywhere, send me an email. Try to get this done as soon as possible. I may not be able to record the homework. We're not done yet. Superman is coming in. What was I saying? I may not be able to post the video about the homework. So my plan was I would go over the homework problem in class, but there's just not enough time. So I will record a short video and I will post the homework video, those homework problem hints online, and I will add the slide to the class notebook. It's not a long homework. There's only 3 problems in there. There are 3 extra credit problems. That's separate. That's optional, obviously, as always. But the 3 problems in there, I will post hints on how to solve those 3 problems. Okay. And so make sure you check out those videos. But I won't be able to record that video until later tonight. So if possible, I'll get it done early. But more likely than not, it'll be later tonight. So one final thing. Oh, any questions? Steps, methodology, anything? Yes. No, no. In the hint, in the guide that I will post, I think I might recommend that it's easier if you choose this node. That's the extent that I would say. Yeah. The question being asked was, would it matter on the homework problems which reference node we take? And the answer is no. That that applies to any solution with node voltage analysis. Okay, supernode. So not quite Superman, just a supernode. Sounds like a fantastical concept, but it's not. Like voltage and current division, all it is a shortcut. That's all it is. So this example, you see two voltage sources. If it's one voltage source, you choose one end of the source as your reference node, and thus you have an answer for the other end, right? So for instance, if I choose node 1 here as my reference node, then V1 is equal to 0 volts, and V2 would be equal to 10 volts. But what about this 15-volt source? How do we solve this? We can only have one reference node in a circuit. You cannot have more than one. If there is a current, let's call it IS1 flowing through this voltage source, how can we express IS1 in terms of Ohm's law? Actually, the question, more appropriate question would be, can we? The answer is no, you can't. And so first we came up with the concept of supernode. It's very easy, very simple. And I'll tell you, it's not just me saying it's easy because I know how to do it. If A equals X and B equals X, can we say that A equals B? That's all we are doing here. It's a shortcut. You apply KCL at both ends of that voltage source. So you would get IS1 equals something. Then you apply KCL at the other end of the voltage source. So you would get a second equation, IS1 equals something else. You equate both of those together, thus eliminating IS1. Essentially, what you're doing is you're combining both nodes together into one single supernode. You're shorting out that power supply. You run a wire from that one node to the other node or to the other end, and you apply a KCL. So again, it's a shortcut that allows you to skip a few steps. So let me draw this out. 3 minutes left. If you have to leave at 12, you can leave. I will just finish talking and recording about this, and then you can, later on watch the video online. So you have two resistors coming from the top. You have a 15-volt source, minus and plus. And then you have another resistor here. And then you have another resistor on the far left. Those are the only only two connections at the top and only two connections at the bottom. And I'm going to choose current IR1 coming down from the top. I have current IR3 coming into IR4. And then I have IR2. And this, of course, I established as IS1. So let me call this node and this node right here as X and Y. The goal is to apply KCL at both ends. So if I apply KCL at X, I have IR1 and IR3 entering the node, and I have IS1 leaving the node. Right? Two currents enter, one current leaves. Then I apply KCL at the other end, which is Y. So applying KCL at Y, I have IS1 is still coming out of the node. Sorry, not out. Going into the node. IR4 is also going into the node, and IR2 is leaving. So I have IS1 coming in IR4 coming in, and IR2 leaving. Rearrange the terms. I get an expression for IS1 as IR2 minus IS1. Oh, IR4. Then I equate the two together and I obtain IR1 plus IR3 equals IR2 minus IR4. That's it. If I was to combine it together in a super node, this would be the circuit diagram. Voltage source is shorted out, right? All of this is one single node now. So in this one node, I have IR1 coming in, IR3 coming in, IR4 coming in, and IR2 leaving. So if I apply KCL at that super node, I would obtain IR1 plus IR3 plus IR4 equals IR2. Exactly the same expression. Yes. If you have more than one voltage source, because we cannot write an expression for the current through that voltage source. Yes. Sure. Shortcut. That's all it is. Let me note it down here. So as I said, it's not some fantastical concept. Just because it says super, it does not mean it's going to be super. As with the recent Marvel movies, this is simply a shortcut. Okay. And it's only, you only need to do this if you have more than one voltage source. Circuits with more than one voltage source. Current source does not matter. The previous example had two current sources. We can solve it fine because current source has a value. When we apply KCL, we can simply plug in the value of the current source. Okay. All right. We'll end class here today. Homework due on Sunday night and quiz on Monday. If you have any questions, I'm available right now. I will go back to my office, and as soon as I reach there, I'm going to download the videos and post it. And then office hours between 4 and 5 today. And I will see you all on Monday.